Good morning. Welcome to episode number 25 of the ZoomTown experiment. Hopefully I got the episode number right in this particular episode. I also got a new t-shirt. Check this out. How's that for styling? Well, we're picking up today from last week's episode where we did all the framework or getting things ready for MQTT communications and getting the networking established and set up and configured, etc. So I'm not planning to really rehash a lot of that data today. In fact, most of the code that we're going to talk about today is in the program from that last episode, but we're just going to enhance on it a little bit and then show it in operation working with the scheduler computer. So let's dive right into the code here on the Pico W. All of the code is the same. I haven't changed anything in the configuration of networking and MQTT comms. We will be talking about this one in more detail a little bit later, but again, it's not changed. Same thing in this area, and then our packet function. And just as a quick reminder, the packet function uses a join command. And that is a very efficient way to take all these variables and pack them into a list so that it's very easy to unpack them once we transmit this over to the scheduler. And I hope to have time to go into that and show you the time difference, how efficient this is over just doing a simple combining of those variables. Let's get all the way down to our main loop because that's going to be the bulk of our focus today. Let's see, what do we got here? Okay, some of the things I've added in, these three variables here, which are also in here, but only get executed every sixth cycle through the main loop. We don't want to be transmitting MQTT data any more than we have to, so that was my regulator to slow down that process. But I needed these variables to be set to 0 because they're not counted every time. And that'll make a little more sense in a moment here. But as we come into this, every sixth time through the main loop, we will record the current time. That was added in from last week. I need a baseline here, or a starting point. We're going to also use the variable POS position, and I'm just going to incrementally bump that up each time through the loop, just so that we see change at the receiving end on the scheduler. We're going to pack all of these variables, here, 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 and here, into the variable message. And then I'm going to record the time it took to do that. That'd be the time from here to here. Yes, I know that guy will be counted in it too. It's only a few microseconds and I'm not worried about it. Then we will publish that command or that variable list over to the scheduler, and that will then be, the time for that will be measured between CP5 and CP4. So we'll see how long it takes to perform the packet operation as well as the publish operation. And we'll also be seeing the runtime of the whole loop when we print this out and run it. Beyond that, I don't think there's much more in here that's any different. I've modified the code here a little bit on the print statements. And what I'm doing, I'm getting the time it took to do the packet operation with this function, and then the publish it in this function. And that's just taking the current time minus the last time, the time, start time, if you will, and then repeating it for our publish thing. I will then print out the word pub telem, the packet, the pubit variables, and then the full runtime for the whole cycle of the main loop. And we'll go ahead and run this, and we'll stop it pretty quickly so we don't have a bunch of data to look at. Okay, so you saw that. Pretty quick. A lot of data happens real fast there. So I'm going to bring this up, and we'll go back to the top of that list here, or the top of my printout so we can look at the data. We'll drop in, let me go down a little bit more. one more. Okay, so now here we are. Let's just pick up on these lines here. So this would be once through the loop, another time, another time, another time, another time. And at this point, we're performing the packet operation to combine those multiple variables into one variable that we would transmit via MQTT. And then that was 799 microseconds. And this one is 614 microseconds to actually transmit the MQTT message. Now, it's obviously a long time compared to some of our sensors, but there's an awful lot going on to make this all happen. I was surprised that just packing variables would take so long in Python, and there might even be yet a faster way that I haven't discovered yet, but I'm fine with accepting it as it is. But now you'll see how that main loop will always be essentially at 5 seconds, even though here I've added almost a second, or 5 milliseconds, and here I've almost added a millisecond and a half. So this is our deterministic loop performing as I want it to. And this also is showing you how the data is transmitted. Now, coming up next, we're going to look at it from the other way. From the scheduler computer, we're going to pass data back here to the Pico W, which is powering and controlling our Zoomie. So let's dive into that. All the way back at the top of the program is our receiver callback function. And this will take the data coming in via MQTT from all the topics that we subscribe to, and then we'll process it and handle it here as well. The thing to remember, I'm going to have 16 Zoomies on the table, and they're all hopefully going to be working at the same time. Now, some of this information coming from the scheduler will all go to all the Zoomies at the same time, specifically cycle start, feed hold or emergency stop, and then our feed rate override. That gets sent to all the different Zoomies, and all the Zoomies will subscribe to that. The information that won't come that way to everybody will be driving instructions. For example, if a Zoomie is sitting in a driveway, and the scheduler wants to schedule that Zoomie to go to a location at a specific time, it will send it a packet of information for driving instructions. Those driving instructions should only be sent to the intended receiver. That is how the MQTT system works with subscribers or subscriptions. We would subscribe to the driving instructions for this particular Zoomie, which I believe we ID'd it as Z%. That's its secret name. So that'll kind of start making more sense once we have more Zoomies in play. But for right now, let's just take a look at this function. We're going to deal with a few global variables that we'll be setting. SV_CS is our cycle start. SV_OR is our system variable override. And then ESTOP _S, and that is again for system. So that is where the data will be set, and then the rest of the program will act upon the change of that variable. Incoming, we will be getting a topic and a message. The topic has to be decoded, as will the message. And there's a lot of funky stuff on newer programming languages that we didn't have back in the day. It was all basic ASCII data. So we got some encoding and decoding that you have to deal with. Now at this point, we're going to look for specific topics specific topics, but it's a longer message than just ESTOP in this case. There's other data in there. So we're looking at a sub portion of that from element 3 to 10 for ESTOP. So if we see the topic ESTOP, if the message coming from the scheduler says stop, I will set the ESTOP variable to 0. and print a note that it was pressed down over at the scheduler. Likewise, if there's a message is reset, that means we are no longer in an emergency stop situation, so we're resetting it. In other words, the e-stop switch would be pulled up. We would then print out that message showing that state. And of course, these print statements are strictly there for debugging and development. Going on to the other button for our discussion right now will be the cycle start button. Again, that would be a topic. We're looking at the topic cycle start. And we want to set the system variable. If it's currently set to start, we will set the system variable cycle start to 1. And again, print out that state. When the button is released, we will call it hold, and we'll set the system variable to 0. Now, elsewhere in the program, remember, this loop is running constantly. If it sees a change in that state, it's going to perform an operation, or based on that action. Next up is our velocity override. This will allow me, at the scheduler, to override the speed of all the Zoomies simultaneously from 100% all the way down to 50%. And right now I've got a little trick in the code so that at 50% over on the scheduler, that's how I break out of a loop. We'll get by that as development continues further along. But again, same as before, we find the topic of velocity override, but this time the message we need in numerical data. So we want to convert it to a float. And if that variable data is less than 0.6, we'll set the system variable to 0, meaning go all the way down to 0. That was kind of my trick I was mentioning a moment ago. And then we'll print out that we're at a velocity of 50% or slower, and that will actually end up just stopping all the Zoomies right where they are. Otherwise, if it's any other value, which would be 0.7, 0.8, 0.9, and 10, we will then set the system variable override to the value being sent by the scheduler to the specific override percentage. It seems super complicated, but it's truly very, very simple. So what we'll do, we'll go through and demonstrate these three functions. I will hold off on demonstrating the transmission of the driving instructions until much further along. So we'll be leaving that part out of this discussion. So I'm going to get this all kind of set up so we can see what's going on. I'll get that up a little higher. What we're going to be looking at to start with is an e-stop command. I need to do that over at the schedule, so I'll go over there, pop down the e-stop button, and then we'll see what the incoming message and how this handler deals with it. We'll get the program running over here. I'll clear all this data out, clear it. And now what we're going to do is we will go over to the scheduler. I'll hit the e-stop button, and we'll see the behavior over here on our Zoomie. E-stop went down. We received the message that the e-stop button was pressed down. It's a latching switch, so it stays in that state. Now we'll release it. The switch is up, and we get the release on this end. Now we'll do the same thing with cycle start. I will press the button down, hold it for a second, and then release it. That is a momentary switch. So let's see how we interact with it here. And as you can see, we receive the information, we deal with it, and we move on. And finally, velocity override. Now what I'll do on that one is I'll take it from 100%, 90, 80, 70, 60, and then right back up to 100% again. That's a rotary selector switch, so it has very discrete inputs. It is not a rotary encoder switch. So let's see how that behaves. And as you can see, it works just like the other ones, where we get a discrete change in state for each setting. So with the MQTT and the networking and all of this, it gives me an easy way to deal with communicating between all the devices. It also appears to be fairly efficient. So I will go through and I'll document this up, and then we'll discuss that in the header comments that I'll create. Now I want to go through and measure the cycle times for each of these operations. And to do that, I've gone through, added a getIt variable to measure the time for getting the message, part of our whole MQTT process, and then we'll print that out. So we'll see our packet, our pubit, and our getIt of the data, and then the full loop runtime. Now, one thing I wanted to point out, up here in our code for handling the messages, I commented out the print statements for the cycle start function. Print statements can take a very long time in MicroPython, a very long time. And I don't want that influencing the time it takes to process this particular data. So I've commented them out, and to be able to detect where that happens, I've added to our main loop down below the if system variable cycle start equals 1, break out of the loop. So I'll know it's the very last action that is performed. So with that, let's go ahead. I'm going to get everything running here. Okay, we're processing data. I'm going to the scheduler. I'll hit cycle start. And at that point, our loop ends. Now, what we can do, I'll try to zoom that up bigger. Hopefully it'll be a little more visible. Don't worry about that alarm there. That's outside of our main loop. As it was running, we were at 5 milliseconds all the way through. It never changed for all the work that it was doing, especially when we actually handled the MQTT communications, which is that line there. So it took 658 microseconds to pack the message for transmission, 804 microseconds to transmit the message, and then it took 1,000 microseconds, or 1 millisecond, to go through and handle the cycle start button action. Now, that might seem like a long time, and frankly it is, but this doesn't happen very frequently. It's very rare that I would be over at the control panel hitting cycle start or e-stop or the feed rate override. So these are pretty unimportant tasks regarding time. Nonetheless, I still want to track everything. So I'll get this data up in my header, and then I'm going to clean up this program kind of back to the way it should be so that we're ready for our next episode. As you've been following along with the ZoomTown experiment, you've been noticing I pay a lot of attention to how long things take to execute within the program. The larger and more complex a program gets, the more critical it is to pay attention to the little details. For small knockabout utility programs, these aren't real important aspects, but when you get into this level of a program and you're going to push the boundaries or limits of performance, it becomes very important. And because of that, I wanted to take this sidestep part of this video to talk about how I looked at this function that I needed to compact several variables into one thing very quickly so that I could also transmit just the one message instead of 5 or 6 individual messages. All around, this was a very huge time savings. So to me, it was very important, and I'd like to share that with you, my approach on what I had done. Now, the first idea I had for combining together the data in our packet, currently we saw it as the packet function. We need to combine together the direction, marker, control, velocity, and odometer variables. So I originally went about that using a fixed format type packing. And I've done this in years past in many other languages and never really paid attention to how long it really took. In those applications, it wasn't important. But I do want to show you here how long it does take. And we'll run it first, and then I'll show you the code afterwards. So we will run it. And it took 1.714 milliseconds to take those 5 variables and pack them into the string that you see here. Now that seems pretty chaotic. What does that mean? Well, to unpack that, I will just copy this like so. Copy it, and then I'm going to move it up here, or actually down here somewhere, where we've got some blank space. And I'll show you how I would have unpacked that. Direction, marker, control, velocity, and odometry. Each of the elements of that string are a specific exact length. My direction is always 1 character, as is the marker and the control. 1 character, 1 character, 1 character. So I could easily extract those using substring. Then my velocity and my odometry, I managed to make those, I stretched them out, padded them with extra zeros so they are a fixed length. And if you read that mathematically, that's still 3.1, and that is still 1.96, even with all the extra zeros. So this methodology I've used many times in the past, and it's worked perfectly fine. I never worried about 1.74 milliseconds to either pack or unpack it. It wasn't critical. Well, in this case, that is critical. That's a lot of time. And the way this function worked out for me, I would take in, well, let me show you where we call it here. I'm saying x equals get packed. Direction, marker, control, velocity, and odometry is passed into the function. That is here. So with the velocity, I need to pad that with extra zeros. So I call the function pad, passing in the string here, s. I added all the zeros at the beginning, extra zeros at the end. I find my decimal point, and then I work back from there to either, if the value is 0, just provide back 000.000, 3 decimal places, 3 decimal places. Or I, from the decimal point, break out my substring, -3 or +4, because of the way substring works. And then I return that value, which will be formatted as such, back to here. I do the same for odometry. Then I pack everything together, adding the strings together. Directory, marker, control, velocity, and odometry. And then I return that. And yes, I could combine that and make it a teeny bit faster. But that methodology took 1.714 milliseconds. And in my case, that's a long time. So I checked around within Python to see if there were other functions. There had to be something else out there where I could kind of throw a bunch of data at it and it'd make it small and compact and also be able to unpack it. And that's where I found that join statement. I've never seen it before, never used it until I got into this problem. So now let's see how that one works. So I'll go through, comment this guy out, uncomment all these guys, and I'll delete out this stuff down here. That was my little example. So now we will just run it, and this is what it spits out. We can see that there's F, kind of like a space, 0, space 1 space 3.1 space 1.96. Again, it breaks out very much like our previous example, but there's a little bit more magic to this, and we'll see that in the unpacking sequence. Now, here's the other thing. That only took 834 milliseconds. That's a lot faster, nearly twice as fast. And in some of the other experiments with repeated calls to it, it is actually even faster yet. So this is what I'm focusing on with trying to find shortest times and really knocking out any waste. In any operation, get rid of waste, and it's free benefit, right? Now, there are times when I won't really push the bounds on a lot of getting every microsecond out, because to me it sometimes makes the program so difficult to read, I can't understand it a month later, oftentimes a week later. So I do practice both sides of the coin here. I want to be efficient, but I also want to be able to understand my code. Now, I had mentioned that unpacking it, if you can pack it with this join, there's got to be a way to unpack it. And any variable in Python or MicroPython has a split function. And if I split using the hashtag character, which is what we used, let's go up here, to join all of these variables, we can then assign that to a variable that's a list with all these elements, and then I can get the local variable to make it easy to read what's in each one of those, and then we print it out. Now we'll look at that again here, up here. This is what it looks like unpacked, and then this is what it looks like packed. There's our hashtag codes, and then this is unpacking. So it's a very fast, clean, simple process. To me, again, it's important. I'm sure you will run into projects that require this level of attention to detail. But remember, it's always a balance. You can make things super efficient, but then readability might go down or usability might go down and all of that. In my position where I need to communicate this, I try to go with code that is more readable, even if it is less efficient whenever possible. So again, Zoomie 03-A is the program that we discussed today for the Zoomie. And then this pack time function, I'll include that in the packet of data that you can download off of the companion website, makingstuffwithchrisdayhut.com. I could have made the name a little longer, but I thought, nah, you guys are okay with that. Now moving on to looking forward to next week. Next week, things actually start moving around. The focus of next week's episode will be to get the Zoomie moving around. Somewhat primitively, but it sets the stage for refinement. So most of that will be filmed here at the electronics bench. We're not quite ready yet for going out on the test track. This should wrap it up for this video, because I'm quite sure I got it a little bit too long again. But thanks for sticking around and watching, and I look forward to seeing you next week.